Hello everyone, my name is Balan and I'm a final year PhD student in AI. I will be presenting alongside my colleague Tim Wood, who is a cryptography engineer. Our paper is called A Framework for Cryptographic Verifiability of End-to-End AI Pipelines, and we conducted this research during my summer internship in 2024 at Digital Catapult, which is a tech innovation organization partly funded by the UK government. Before diving into the details, I want to be clear about what this paper is and what it isn't. This work does not present a one-stop solution for trustworthy AI or a full technical solution. Instead, what we've done is map the problem space, review the tools we already have, and propose a conceptual framework to help align ongoing efforts towards interoperable, cryptographically verifiable AI systems. We hope it provides a common ground for researchers, engineers, and regulators, especially as the demand for trustworthy AI becomes non-optional under laws like the EU AI Act. Let's take a look at a traditional AI pipeline. First, raw data is collected, which is anything from images, text, to sensor readings. Next, the raw data is analyzed, cleaned, and pre-processed. And we check if the data is balanced or biased, and then we turn it into a form that the AI model can understand. Then comes the model training step, after which the model's performance is evaluated on previously unseen data. After that, the model is deployed into the real world where it can start making predictions or powering apps that users interact with. Finally, sometimes the model needs to unlearn, which means removing the influence of certain data points from the model. Even within the same organization, keeping track of all these stages and ensuring they're done correctly is already a complex challenge. However, today's AI systems operate through modular, loosely connected stages, with these steps often happening across different companies, organizations, departments, or even across different territories. Each company and territory has their own processes, standards, and more importantly, regulations that they need to comply with. This fragmentation makes it even harder to guarantee transparency, accountability, and compliance throughout the entire AI pipeline. I will now provide a few examples of relevant regulations that model developers need to comply with. The EU's Data Governance Act impacts early stages by setting rules on how data can be shared and used responsibly across organizations. When it comes to personal data, you have laws like the GDPR in the EU, PIPEDA in Canada, and the CCPA in California. They all put strong privacy rules in place, including the important right to be forgotten, meaning individuals can ask to have their data deleted even after it's been used for AI training. The EU AI Act covers nearly every step of the pipeline. It focuses on managing risks, ensuring transparency, and making sure AI systems can be audited properly. So you need to track what's happening at each stage from training to deployment. Then, the Digital Markets Act and the Digital Services Act in the EU regulate how AI services run on big online platforms, pushing for fair competition and transparency. Finally, there's sector-specific or national laws like HIPAA in the US, which affect certain pipeline steps depending on the type of data or industry. While the AI pipeline's modularity is convenient for engineering and scalability, it creates additional problems around verifiability and traceability. If a dataset is tampered with, or if a model is poisoned, these issues are often undetectable downstream, especially when the pipeline is distributed across vendors or outsourced services. Additionally, while the models may claim benchmark performance, these claims are not independently verifiable. The EU AI Act, for instance, requires transparency regarding training data and model performance. At the same time, many AI providers are reluctant to expose commercially sensitive training data or proprietary model architectures. So we're seeing a growing tension between regulatory demands for transparency and the industry's confidentiality. This motivates our research into cryptographic verifiability for AI pipelines, methods that allow us to prove compliance without revealing sensitive information.
So Kara's highlighted the drawbacks of the AI pipeline. In our work, we were looking at how to use cryptography to provide some level of assurance on different parts of the pipeline, such as proving the provenance of training data and that processes like training have happened correctly. So what is the cryptography we're considering for AI verifiability? Well, cryptography is used all over the place in digital systems for protecting data, but we're just going to focus on 3 tools for our pipeline. And the first one is cryptographic commitments, which are a way for somebody to declare that they know some information without revealing what it is. And the point is that somebody produces a commitment so that later on somebody can verify it if the data has been revealed, so that proves that the data hasn't been changed since that time, or it can be combined with other types of cryptography to prove information about the data without revealing it. The second is digital signatures, which people are probably familiar with, which is to make a mechanism to make sure that data is authentic, that it comes from the purported source, and that it hasn't changed in transit. Thirdly, we have zero-knowledge proofs, which are a way of checking that a process was performed honestly. And crucially, it does that without necessarily revealing the data that was computed on, and also without the computational overhead of the actual computation itself, which is important in the context of AI pipelines, where, for example, you've got to train the model, which is a huge computational burden.
I will now walk you through our proposed framework for end-to-end verifiable AI pipelines. The top row in green represents zero-knowledge proofs, which provide verifiability of each of the processes' integrity. The bottom row in orange represents cryptographic commitments to data objects, such as training data or trained models, which are inputs or outputs from the zero-knowledge proofs and their respective processes. The idea is to generate and verify proofs that each process in the pipeline has been executed honestly and that inputs to each process match public cryptographic commitments to the outputs of the previous processes. Linking zero-knowledge proofs together using commitments is already being done for some parts of the pipeline. However, there are still gaps, which we will discuss later. In these early stages of the AI pipeline, we focus on two things. First, ensuring that the raw data we start with is authentic, not tampered with, and that we have creator consent. For data authenticity, the Coalition for Content Provenance defines an open standard for embedding provenance metadata in any type of digital media called C2PA. Signing involves creating a cryptographically verifiable manifest that is bound to the asset, which can include details such as authorship, capture time, and even AI training consent. This manifest also includes a cryptographic hash of the asset, known as a hard binding. If the asset is tampered with, the hash no longer matches and verification fails. Then, in step 2, we want to prove that transformations like resizing or cropping are faithfully applied, because even small changes here will mean that the inputs no longer match the public cryptographic commitments, which opens the risk of training on potentially manipulated, biased, erroneous, or copyrighted data. Zero-knowledge proofs then enable an editor to cryptographically prove that an edited image corresponds to a signed original, all while keeping the original private. This is achieved by designing a zero-knowledge proof circuit that takes as input a commitment to the original image, which is typically a hash or a signature, the edited image, and then the circuit of the transformation. As an example, ZK-IMG is a state-of-the-art system for doing this efficiently at HD resolutions, and it supports a wide range of transformations and keeps proof generation and verification practical even on commodity hardware. Then, zero-knowledge proofs of training enable stakeholders to verify that training was conducted correctly using a specific dataset and algorithm, providing confidence in the model's development process whilst keeping the privacy of the training data and the model weights. However, zero-knowledge proofs of training do not hide the training process itself, since it is essentially encoded in the public verification algorithm. Recent significant advances in the field have enabled zero-knowledge proofs of training implementations to produce proofs within acceptable time and size bounds. ZK Audit, for example, can generate proofs for a mobile net model in less than a minute, and verification takes a few milliseconds. This progress now opens the door to practical use cases, including privacy-preserving audits, regulatory compliance, under frameworks like the EU AI Act, and trustworthy machine learning as a service platforms. Zero-knowledge proofs of training can also be used to prove that fine-tuning of models has been computed honestly, and they also have applications in federated learning, which is a distributed type of machine learning. Now, zero-knowledge proofs of inference enable a party to prove that an AI model has made a correct inference and that a specific previously committed to model was used without revealing the input or the model weights. This solves a common issue in traditional pipelines where inference is delivered via opaque APIs. Users have no way of verifying which model versions was used. Providers might silently swap in faster or low-quality models. In addition, proofs can also be generated to enable verification of model performance on benchmark datasets. These proofs allow for the private aggregation of model performance metrics, ensuring verifiable evaluations without revealing sensitive data. Several works can now generate proofs of inference for large-scale models, such as Stable Diffusion and NanoGPT, with proving times ranging from 46 seconds to an hour and verification times of 2 seconds and less. Tools like Ezekiel make it possible to automatically convert models to circuits and generate proofs for any ONNX-compatible model. And then finally, zero-knowledge proofs of unlearning enable the verifiable removal of specific training data points from a specific model without disclosing that data or the model weights, which is crucial for compliance with data protection requirements like the right to be forgotten. Eisenhower's is the first and only system to provide cryptographic proofs for both training and multiple types of unlearning. Proof generation times vary between 53 seconds and 5 minutes per data point, and proof verification takes between 20 seconds and 2 minutes. So now we have seen the tools which enable verifiability across the entire pipeline. Unfortunately, while the tools exist, they have not been built in an interoperable way, and gaps remain along the pipeline.
So we're now going to have a look at these 3 gaps in the AI pipeline. The first gap is between the raw data downloaded as datasets or from web pages to the refined dataset that's actually needed for training. And filling this gap can be straightforward. For example, if you use an AI model to filter the data, then you could provide a zero-knowledge proof of inference to show that you filtered honestly on the data that you ingested. But obviously, we'd want to verify that the filtering AI was trained correctly, possibly involving another verifiable pipeline. But there are other ways to filter data too, so we don't get a circularity problem. The point is that you can prove that you haven't introduced bias by carefully down selecting your training data using a technique like this. The second gap is between the refined dataset and the actual numeric inputs to the training algorithm. The idea here is that images that are protected with digital signatures and used in C2PA are often in image formats that use compression or aren't the right size for the training algorithm, things like that. And we want to be able to say that the data used for training is an honest representation of the refined dataset. So what we can do is we can use the zero-knowledge proof to prove that these transformations have actually happened honestly. And clearly, if you don't really care about the privacy of the training data, you don't need to do this in zero-knowledge. You could just do this in the clear. You might just produce commitments to your training data at this stage. So the first 2 gaps we've looked at are towards the beginning of the pipeline. The last one we'll have a look at is at the end when we're obtaining model inference. And the point here is that the most zero-knowledge proof of inference tools take the plain set of model weights as input. But how do we know that these weights actually correspond to the model that was trained, right? The proof of inference is completely meaningless unless we know it corresponds to the model that was actually trained honestly. And what you want to do here is to have the zero-knowledge proof of inference take a commitment to the trained model as input to provide that link with the zero-knowledge proof of training from before. And the challenge, and I think probably the reason why it hasn't received a lot of attention before, is that the zero-knowledge proof systems that are optimized for training are not always sort of readily compatible with those that are used for inference. But there has been some work to show this is possible. The ZK audit is a good example of this. So here's an overview of the whole pipeline, and I'm just highlighting here the gaps 1 and 2 at the beginning and gap 3 at the end. But once we have these gaps, we've filled them. We've basically got a fully verifiable end-to-end pipeline. So to conclude, while we've seen lots of tools to verify specific parts of the AI pipeline, we've not seen any that address the full pipeline so far. And we think this provides motivation for standardizing zero-knowledge proofs. There are some efforts already, such as ZK proof, and to some extent the NIST threshold cryptography process that's currently underway. We also think that there are perhaps opportunities for regulators to be involved, for example, in verifying the signatures and proofs that are produced as part of this verifiable pipeline, which may help people comply with various bits of legislation. And lastly, our work has identified a few gaps which motivate some future research and provide some direction there. So lastly, just to say thank you for your attention, and please do be in touch if you're interested in finding out more.